Okay, Chem, let's continue on with how to actually draw these compounds. And if you remember back from first year, you would have been taught to draw Lewis dot diagrams for each of the elements on the periodic table of the elements. So you might also remember the octet rule, meaning that everybody wants 8. And we're going to throw that around, but before we do, we're going to go over some crucial exceptions. First of all, let's talk about fewer than 8. Well, hydrogen is atomic number 1, so when you have an atom of hydrogen, it has 1 electron. Now, it's in the first principal energy level. In the first principal energy level, you only have hydrogen and helium. So therefore, the first principal energy level only holds 2 electrons. It has that S sublevel. So hydrogen can either have 1 electron as an atom, it can have 0 electrons as an H+, and it can have 2 electrons as an H-. Those are the only 3 choices. Under no circumstances will you ever give hydrogen more than 1 bond. So he has to live with 2 because that's the first principal energy level full. He's all good and happy. So never, under any circumstances, give hydrogen any more than 2 electrons or 1 bond. Remember, a bond is a pair of electrons. So it is always what we call a terminal element. And then let's go to family 2. We've got beryllium here. Beryllium, you might say, is technically a metal, but it's right next to boron, which is a nonmetal, and he'd actually be considered a metalloid of sorts. But when he forms bonds, he only has 2 electrons. He cannot pull any more electrons out of nowhere to form bonds. So he'll form 2 bonds, and he's got to be happy with 4 electrons. Boron is in the next family. That's group 3. He has 3 valence electrons. So here is his dot diagram. And again, like beryllium, he cannot form more than 3 bonds with his 3 electrons. That's all he can come up with to form bonds. So boron is always going to be happy with 3 bonds. He's going to have 3 shared pairs, and his 3 shared pairs are going to give him a trigonal planar. He has no lone pairs of electrons to warp the bonds, so he's always going to be trigonal planar, and he has symmetry. Therefore, he will form a lot of nonpolar compounds. Let's go to our super important guy next, carbon. Remember, we went over sp hybridization, so he'll start off with 2s and 2p, but when he goes to bond, he will hybridize, and he will have 4 electrons with equal energy. These 4 electrons with equal energy are going to form 4 bonds. So carbon, he's notorious for being a central atom. He is notorious for forming 4 bonds, whether it is 4 single bonds or 2 single bonds and 1 double, or 1 single bond and 1 triple bond. So he always forms 4 bonds, and as long as the atoms that are attached to him are exactly the same, identical, he can also have symmetry. His shape will be tetrahedral. Next, let's go to nitrogen. Nitrogen has 5 valence electrons. So he's 1, 2, 3, 4, 5. In order to get to 8, he would want to have 3 more electrons. Therefore, he'll form 3 bonds. He forms 3 bonds and has 1 lone pair of electrons, and that will warp the bond down. He will be what's called pyramidal, trigonal, pyramidal. So because he's a pyramid shape, he can never have symmetry. So nitrogen is highly electronegative. As long as he's bonded to somebody who's less electronegative than him, then he will be a polar bond and polar molecule every single time. So you can't have symmetry with this guy. So this guy can have symmetry, this guy can have symmetry. He can never have symmetry. Let's go to the next one, which is oxygen. He has 6 valence electrons. He wants 2 more, so he has 2 empty spaces, so he'll form 2 bonds in order to get those 2 empty spaces full. This is the reason why water is a bent molecule and not linear. So water is not a linear molecule. That's why water is a polar molecule. And you'll notice, remember, we want a red flag to go off. Hydrogen bonding is fun. So we have a hydrogen and an oxygen. This leads to hydrogen bonding. So this guy and anybody in the family who's like him is going to be bent. And when you are bent, you have 2 lone pairs. You can't have symmetry ever. So these, as far as symmetry goes, symmetry, symmetry, no symmetry, no symmetry. And then my last one is my halogens. Halogens are also typically terminal elements, meaning that they only have space for 1 more electron, which they will desperately try to find. So the halogens typically form 1 bond, making it a linear molecule. And if the bond is polar, then the molecule is also polar. So you're not going to get symmetry with this guy either, unless it's a diatomic element. Our next concept is expanded valence. This is when the central atom has more than 8. And this can happen if you have access, if an element has access to a D sublevel. So anybody in the first and second principal energy level, you cannot overload. So never give carbon more than 8, never give nitrogen more than 8, never give oxygen more than 8, and never give fluorine more than 8. So this is only applicable to elements that have a D sublevel, therefore third principal energy level or greater. So I'll go over again how you decide that. So the outside atoms never can overload, but the inside atoms can, and only if the inside atom has access to a D orbital. And then there's odd electron compounds. There's a few stable compounds that contain an odd number of valence electrons and then can't obey the octet rule. These are going to be a little goofy, but you're still going to follow the same exact rules, and I'll go over those rules next. So how do we draw compounds? First of all, hydrogen is always a terminal atom, and usually any of the halogens. Always remember that hydrogen can never have more than 1 bond. You can never give hydrogen more than 2 electrons. Then you got to figure out what is the central atom. The central atom is always the element that has the lowest electronegativity. In most compounds, they'll be written first. In most compounds, they'll occur the least often. So there'll be some other clues also. The next step is to add the number of valence electrons in the compound. Once you add the number of valence electrons in the compound, that's exactly how many electrons that you will represent. No less, no more. every single time you need to represent every electron a compound has, no more or no less. If you are trying to represent an ion, remember that a negative sign means that I have one extra electron. A positive sign means that I have one electron short. So if you have a minus ion, that's how many extra electrons you have. If you have a plus ion, that's how many electrons you are short. So you draw the central atom surrounded by the other elements in the compound. You bond them together with a single bond, and then remembering that every single bond is 2 electrons, you add up the number of electrons that you have used. Next step is you satisfy the outside atoms with the number of electrons that they want. So remember, hydrogen would want 2, and all the other outside ones are going to want 8. If the central atom is not yet surrounded by 4 electron pairs, you're going to have to turn one of the lone pairs of electrons on the outside atom into a double bond. Let's see if we can figure that out. So HF. First, I add up the number of valence electrons. I can find that by the Roman numeral at the top of the family. Hydrogen has 1 valence electron. Fluorine has 7 valence electrons. So I have a total of 8 electrons. That's how many I need to represent, no less, no more. When I bond them together using this single line, I used 2 electrons. Now I have 6 left to do. Remember, hydrogen can only have this one bond. He's already got 2. He's got the maximum he's holding. So I'll take the other 6 and satisfy fluorine. Fluorine is highly electronegative, so this is going to be a polar covalent bond. In order to be complete, you would need to draw the partial negatives and partial positives. This is a linear molecule. This does not have symmetry, therefore, it is a polar molecule. B, N2. Well, each of the nitrogens has 5 valence electrons. So I'm add them up, and I have 10 electrons I need to represent. So let's write this guy down, bond them together, and I've used 2 electrons. I have 8 left over. You're going to start to recognize, oh, geez, okay, so 2, I made this nitrogen happy, but this nitrogen's not going to be happy at all. He only has 4. He would need 6 more. So this is when you say to yourself, I don't have enough electrons. So what you need to do in this case is draw a double bond. Now, that double bond uses not 2 electrons, but 4 electrons. So let's do a double bond. I represented 4 electrons. Now I have 6 left over. I can recognize, oh, I can give them each 3. They're not going to be happy then either. So let's make this a triple bond. And I'm going to do a spoiler alert for you. Triple bonds are 6 electrons. Nitrogens love triple bonds. Because they have 5 valence electrons, they need to share 3 more. They do that a lot of times. Now I have 4 extra electrons, which is perfect, because each of these nitrogens had 6 and want 2 more. And I can double check that I represented all 10 of my valence electrons. 2, 4, 6 with my triple bond. 7, 8, 9, 10. I'm good. This is non-polar because each of the nitrogens are identical. C is NH3. N has 5. I have 3 hydrogens that each have 1. So I have 8 electrons I have to represent. Obviously, hydrogen is a terminal atom, so hydrogens always have to go on the outside, no matter what you're drawing. I will bond these together, 2, 4, 6 electrons I used, and now I have 2 left over. You've got to make sure you're keeping track of them because you're going to be wrong if you don't use all the electrons that you have. In this case, hydrogens are happy. So my 2 extra electrons belong here, which makes nitrogen happy now because he has 2, 4, 6 bonded electrons and 2 lone pair electrons. Now, red flag going off, hydrogen bonding is fun. Fluorine, oxygen, nitrogen. This is a polar molecule, and he will participate in hydrogen bonding, either with other ammonia molecules or maybe with a water molecule. And remember, he is a pyramid. You'll hear him called trigonal pyramidal. So therefore, these polar bonds cannot have symmetry. Therefore, it is a polar molecule. Going on to D, CH4. Carbon has 4. Each hydrogen has 1. So I have 8 electrons to represent. We'll put hydrogens on the outside because hydrogens have to be terminal atoms because they can only have 1 bond. Then when I bond them together, I'm going to use 2, 4, 6, 8 electrons. This is symmetrical. It is tetrahedral. Even if it did have polarity, the polarity would be canceled out by the symmetry. Tetrahedral molecules are symmetrical as long as each of the atoms attached to them are the same. CF4 is E, which I'm doing next. Carbon is 4. 4 fluorines each have 7, 28. So we have 28 plus 4 is 32 electrons to represent. Carbon is the least electronegative, and fluorine is going to be terminal because it can only form 1 bond. 2, 4, 6, 8 electrons I've used, leaving me with 24 left. Which is perfect because each of these fluorines wants 6 more. You give each of the 4 fluorines 6 more. And they will each have 8 and be happy. Now, and this is a case where this is a polar bond. So the bonds themselves are polar, but because each of these is the same, it is a symmetrical molecule. So this is tetrahedral. And it is also non-polar because the polarity is canceled out by the symmetry. Our next one is NO+. So nitrogen has 5 valence electrons, oxygen has 6. But that plus sign means that we're missing one of those. So we only have 10 electrons. So put it together, N and O. Bond them together, and that uses 2. We have 8 left over. You can see that 8 is not going to be enough. In order to make both of these guys happy, I would need to have 12 more. So I'm going to say that's going to be a dead giveaway, because if I use a triple bond like such, that's 6, leaving me with 4 extras. And then I'll go 1, 2, 3, 4. Each of them have the 8 that they want. And then that's how we indicate an ion, as we put brackets. In our next video, we'll talk about Lewis structures for molecules that violate the octet rule.